Right, good afternoon, everyone. I hope that you've been having a really good week so far. It's Friday once again. These weeks just go flying by. I apologize that I couldn't be of assistance to you yesterday. What we're moving on with today is lesson 31.13, which is called the antiderivative of a function, and this can be found on page 3 of your current lesson handout. So I've already alluded to this and mentioned it in a couple of places. What we're doing from here on in is the opposite of what we've been doing to begin with. And in order to help you understand what that means, we have to introduce some new notation here. And the new notation is to use f of x, but we're writing capital F of x. And when I read that for you, I'm going to say capital F of x. So what capital F of x is the antiderivative of f of x. And that's only true if the derivative of capital F of x gives you f of x. So capital F of x is the antiderivative of the function if and only if the derivative of the antiderivative gives you the function. And that should kind of make sense to you because this expression right here is saying the derivative of the antiderivative of the function. Well, I hope you can grasp onto the idea very early here that derivatives and antiderivatives are opposite things to each other, much like squaring and square rooting are opposite things. So if I take an antiderivative of a function and then differentiate that antiderivative, that will take me back to the function. And this is something that you're really going to have to think about. Intuitively, it's very confusing that an antiderivative is something that you differentiate to get the function. I'll say that again. The antiderivative is something that you differentiate to get the function. So that is something you really need to think about. An antiderivative of a function is something that if you were to differentiate would give you the function. And in order to drive that home, we're going to take a look at a warm-up. I've got 3 different expressions. Expression 1 is x to the 5 plus x squared minus 10. Expression 2 is 5x to the 4 plus 2x. And expression 3 is 20x cubed plus 2. I hope it isn't lost on you that if you take expression 1 and you differentiate it, you get expression 2. The derivative of x to the 5 is 5x to the 4. The derivative of x squared is 2x. The derivative of negative 10 is 0. And it probably should not be lost on you that if you differentiate expression 2, you get expression 3. So look at all these blanks we have to fill in. Expression 2 is, well, it's the derivative of expression 1. Expression 3 is the derivative of expression 2. Now, what is expression 3 in relation to expression 1? Well, since expression 1 can be differentiated twice to get expression 3 is the second derivative of expression 1. So let's talk again about this first statement A. Expression 2 is the derivative of expression 1. That means that expression 1 is the antiderivative of expression 2. Expression 1 is the antiderivative of expression 2 because if you differentiate expression 1, you get expression 2. That's confusing, everybody. This is very, very confusing. And what is going to happen throughout the rest of this course is you are going to think that you have a really good handle on things and you will discover that you are differentiating when you should be anti-differentiating, or vice versa. expression 2 relates to expression 3, well, expression 3 was the derivative of expression 2, which means expression 2 is the antiderivative of expression 3. And lastly, since expression 3 was the second derivative of expression 1 must be the second antiderivative of expression 3. This is tricky. Expression 1 is the second antiderivative of expression 3 because if you differentiate expression 1 twice, you get expression 3. It's very useful for you to think of antidifferentiation as being a process, and the process is the opposite to the process of differentiating. So the diagram below illustrates this nicely, I think. We have f of x and f prime of x. We know that to go from f of x to f prime of x requires the act of differentiating, which means that to go from f prime of x to f of x requires antidifferentiating. So if I give you a derivative and say, what's the function? You would antidifferentiate to get the function. We've also introduced this concept of capital F of x. Well, capital F of x is an antiderivative of f of x. So to go from f of x to capital F of x requires you antidifferentiate, which means to go from capital F of x to f of x requires that you differentiate. On this diagram, moving to the left is antidifferentiating and moving to the right is differentiating. All right, I'm going to keep coming back to the idea that the antiderivative of a function is what you would differentiate to get the function. So example 1 says, what is the most general antiderivative of f of x equals 2x? So John is sitting here and John thinks, well, capital F of x is x squared. Because if you differentiate x squared, you get 2x. Marcy's over here and she's saying, well, I think the antiderivative is x squared plus 7, because the derivative of x squared plus 7 gives you 2x. And the idea, and I hope you're catching on to this, is that they're both right. There are an infinite number of antiderivatives to a function. And that's why this question says, what is the most general antiderivative? And what we write for an answer is that f of x equals x squared plus some constant. What is the value of that constant? Well, it's just some arbitrary constant. It could be anything. Because when you differentiate a constant, you get 0. The derivative of x squared plus a constant will be 2x plus 0, which is 2x. You have to try to remember to put that constant on the end of any antiderivative. All right, let's take a look at example 2. We're asked to determine the most general antiderivative. The difficult thing with antidifferentiating is you don't really have a set of rules. But we can take the rules we have for differentiating and try to work backwards with them. Okay, so what we're asking ourselves here is, what do I differentiate to get 12x to the 6? Well, I know that I differentiate an x to the 7 to get an x to the 6. The derivative of x to the 7 is 7x to the 6. Well, that's unfortunate because I don't want 7x to the 6. I want 12x to the 6. So I'm going to engineer this by putting a 12 here and a 7 here, so that when I swing that exponent down, the 7's will cancel and I get 12x to the 6. If you like, you can develop a rule that says the antiderivative of this type of term will have one more on the exponent and we will divide by the new exponent. Let's try that rule here. I'm going to have x raised to 1 more, and I'm going to have to divide by that new exponent. The antiderivative of 3 is 3x, and then plus our constant. So the antiderivative of the function is 12/7 x to the 7 minus 1/2 x to the 4 plus 3x plus c, and that is our answer. If you differentiate each of these terms, you're going to get the original function of 12x to the 6 minus 2x cubed plus 3. B, what is it you differentiate to get 3e to the negative 4x? Well, we have learned that a derivative of e to the is e to the. So we start off by saying it must contain a 3e to the negative 4x. And now what we're going to do is we're going to say, what is the derivative of 3e to the negative 4x? Well, it's 3e to the negative 4x multiplied by negative 4. But we don't want this. We don't want negative 4. When you look up at the original function, there is no negative 4 in front of the function. So how can I get rid of that negative 4? I can divide by negative 4. And if you differentiate negative 3/4 e to the negative 4x, you're going to get negative 3/4 e to the negative 4x times negative 4, and those negative 4's will cancel. Minus, what is the antiderivative of 2 over x? You know that when you differentiate ln x, you get 1 over x. So the antiderivative of 2 over x is 2 ln x. Now, what is the antiderivative of sine? This gets very tricky. What do you differentiate to get sine? Well, the thing you differentiate to give you a sine is cosine. But the derivative of cosine gives you negative sine. We don't want negative sine. We want positive sine. So I need to have minus cosine of x. Now you can check all this. If you differentiate with respect to x, the antiderivative, you have to get the original function. So what is the derivative with respect to x of 3 over negative 4 e to the negative 4x? I'm going to put that negative on the top. It's negative 3/4 e to the negative 4x multiplied by the derivative of negative 4x. Minus, what do you get when you differentiate 2 ln x? You get 2 times 1 over x. Minus, what is the derivative of cos? Negative sine. Plus, what's the derivative of a constant? 0. And this is the original function, which means this is the antiderivative. Our answer is that. C, we want the antiderivative. I'm going to rewrite this function, first of all, with exponential notation as opposed to a radical, and write f of x is negative 4x raised to the 1/2. So this is a really tricky one. When you differentiate, and I've said this a lot, when you wrap an exponent around a base, when you differentiate, the base remains the same. So when you anti-differentiate, the base has to remain the same. The exponent has to go up by 1. But if I were to differentiate this expression right now, I would end up with a 3 over 2 in front of the expression. And when I take a look here at the original function, there is no 3 over 2. So I have to engineer this so that when the 3/2 comes out in front, it will cancel and it will go away because I don't want it there. Now the other problem is that when I differentiate this expression, I'm going to wrap that exponent around the base, which stays the same. I'm going to drop 1 from the exponent, but then I'm also going to have to multiply by the derivative of what's inside, which would be negative 4. And I don't see up here a negative 4 out in front, which means I have to divide by a negative 4. When I simplify this, the antiderivative becomes negative 1 over 6 times negative 4x to the 3/2 plus our constant. So let's check this out. If I differentiate with respect to x, my suspected antiderivative what am I going to get? Well, I wrap that 3/2 around the base of negative 4x, which stays the same. And I'm going to have 3/2 times negative 1 over 6. I drop 1 from the exponent. I multiply by the derivative of what's inside. And then, of course, the derivative of a constant is 0. What we need to do now to finish our checking is to take these two numbers and this number and multiply them together and see what we get. Negative 3 times negative 1 times negative 4 is 12 over 2 times 6, which is 12. The 12s cancel, and I am left with a coefficient in front of this beast of being 1. So this is the answer. All right, D. What we should do with D is rewrite these as polynomial terms. They're not actually polynomials because they have negative exponents, but you get my drift, I think. Except for the term of 4 over x, which I'm going to leave as 4 multiplied by 1 over x. Then we have minus 5/3. Remember that we have developed a little bit of a rule for terms like this one, and even this one. And that's that when you differentiate, you drop 1 from the exponent and multiply by that exponent. So when you antidifferentiate, you increase the exponent by 1 and you divide by the new exponent. This is going to be negative 1 x to the negative 2. And you can see that when you differentiate negative 1 x to the negative 2, you get 2x to the negative 3. Minus, again, you increase the exponent by 1 and divide by the new exponent. This is going to give us plus 3x to the negative 1. And if you differentiate 3x to the negative 1, you will get negative 3x to the negative 2. I left the 4 over x as 4 times 1 over x because you need to remember that when you have 1 over x, the antiderivative is ln of x. The derivative of ln of x is 1 over x, so the antiderivative of 1 over x is ln of x. And you know, even as I say that, I'm rolling that around in my head and saying, geez, is that right? Because it is confusing. I've never been able to be so comfortable with this kind of stuff that it just totally makes sense to me. I have to think about it all the time. The derivative of ln of x gives us 1 over x, so the antiderivative of 1 over x is ln of x. Minus, this will be 5/3 x to the 1, and then plus our constant. And that's it. That's the answer. You could, of course, write this as negative 1 over x squared and plus 3 over x plus 4 ln x minus 5/3 x, but I don't think you need to. If you want to, you can. The last two questions are really, really strange questions. And I would really encourage you to pause the video here and ask yourself what you differentiate to get 3x squared multiplied by e to the x cubed. And if you do that, I will give you a hint and warn you that you're not thinking product rule here. Product rule is for differentiating. What you're just asking yourself is what you differentiate to get 3x squared e to the x cubed. So if you like, pause the video, give it some thought. The answer is e to the x cubed, well, plus our constant. I'd like you to just differentiate e to the x cubed and ask yourself what you get. Well, the derivative with respect to x of e to the x cubed is e to the x cubed multiplied by the derivative of x cubed. This is our u. Well, the derivative of x cubed is 3x squared. But that's what we had to begin with. And we're going to learn a technique of antidifferentiating called substitution, where we can do this algebraically. But once you see that this piece is the derivative of this piece, you're off and running. Similarly, when I take a look at f, now this is going to require a lot of practice and experience, but the antiderivative here is the natural logarithm of 2x squared minus 3, plus your constant. The reason for that is that when you differentiate the natural logarithm of 2x squared minus 3, the derivative of a natural logarithm is 1 over multiplied by the derivative of what you were taking the natural logarithm of. This is our u, and this is going to be our du dx. Well, du dx is 4x. And when you take 1 over 2x squared minus 3 and multiply by 4x, you get the original function. So this is our answer. Okay, so page 408, questions 1 through 7. This is going to require a bit of practice because I've kind of hardwired your brain. I've conditioned you to think in terms of differentiating. So now what you're doing is you're trying to come up with something that if you differentiate gives you what you're trying to find the antiderivative of. And again, as I say that sounds confusing. You really have to slow down and think about this. So I hope you have a great rest of the day, and I hope you have some success with this. If you have problems with it, you can send me emails over the weekend. Speaking of the weekend, have a fantastic weekend, and we will talk to you on Monday. Take care of yourselves.